Okay, so good morning, everyone. Today we're going to be covering, let's see, 28.4, Basic Trigonometric Forms. And we also have to take up the participation question, which I gave on Tuesday. And hopefully I activated Dropbox for that. I don't remember doing it, but I usually just do that stuff right after class. So let's do that one. That was just one question. Oh, and then there's also assignment 1A, which I believe is due next Tuesday, and then we're taking it up Thursday. I think that's the case. Okay, so let's, and let me know if anyone has any questions. So let's start. Okay, share screen, whiteboard. Oh, and if I'm constantly muting it, it's just because I don't want everyone to hear the annoying noises that I'm making. Yeah, so I'm like coughing and stuff like that. So that's why it might be muted off and on. Okay, so first one is, or the only one. So this is participation number 2. It was page 858. And it was number 5. And everyone, please always check out the actual question, like when I write it down at the end of each lesson, because some of these textbooks are different. And I just want to make sure everyone's doing the same question. And to be honest, I haven't had time to look at the first batch of participation questions. Okay, so we have this one. So it is e to the 2x plus 5. And let's do a recap on the formula that we did. What was that? That was the integral of e to the u du is equal to e to the u plus c. Now this one's an interesting one because I just realized there's kind of multiple ways of doing this one, but let's just stay consistent and do what we always do. Let's just check to see if this is in the correct form. So u, of course, is going to be 2x plus 5. And then we take the derivative of that, and let's see what we get. Derivative of u is equal to, so the 5 just disappears, and then the 2x becomes 2, or I should put 2 dx to be technical and accurate and such. Okay, so we need a 2 dx in there. But as we know, that's not too hard to accomplish. You literally just put a 2 in there and then offset it with a 1/2. So let's do that. So e to the 2x plus 5, and then 2 dx, and then 1/2 right here. So that's one of the things that you have to get used to. You have to just know your derivatives, see what you get, compare it to the original integral, and just say, okay, the integral needs that, so I'll just put that in, but you always have to remember in math to balance everything out and offset whatever changes you're making. Because you want to solve an equivalent of the original integral. You don't want to just change it willy-nilly and then solve something different, because that kind of defeats the purpose. Okay, so in this case, the answer should be, so the 1/2 just sits there, and then you'll get e to the u plus c. And in this case, now let's put in our original variables. So this should be 1/2 e to the 2x plus 5 plus c. And yeah, so that is what we get for that one. And so that was it for the participation questions. I'll try to mark those. Hold on, give me a second. I'll try to mark both of the participation questions today. Okie doke. So let's go to the next section. Let's see, should we do this on a whiteboard or the PowerPoint? Let me take a look at the actual PowerPoint for a second. So this one is Basic Trigonometric Forms 28.4. And basically what it is, it's just a list of a bunch of derivative formulas for trig functions. except it, of course, expresses them in terms of integral formulas. But they are all kind of, equivalent to previous derivative formulas we've seen. They're just, of course, the reverse of them. So it's all familiar stuff, just looking like a little tiny bit different. Let's just do, I want to write all of these, so let's do these on the whiteboard. But of course, it's all in the PowerPoint and textbook. Okay, so basic trigonometric forms. So let's just do one example to illustrate where these formulas are going to be coming from. So you might remember that the derivative of sine is cos. So therefore, the integral of cos is, surprise, surprise, sine. And that's one of our formulas. I'm not going to do that for every formula, but this is just to express that they're just very common derivative formulas. And then we're just looking at their integral counterparts. So when I list these formulas, they all have that clear logic of where they come from. So now let's formally list them. So this is sine u, where u is some function, du, equals minus cos u plus c. So that's one formula. And as per usual, you really have to take a close look at these formulas. Notice that it says sine of u, and then just as per usual, it says du right next to it. So you always need it to be in the form sine of some function with the derivative of that function sitting next to it. Or if it's an x, then it'll just be dx. And in that case, you got nothing to worry about. But you do need that du in there. That's important. And then the next one is cos u du is equal to sine u plus c. Next one is, let's see. So this one is just stemming from the fact that the derivative of tan is secant squared. So this is integral of secant squared, secant squared u du equals tan of u plus c. Sorry, I got it muted again. Apologies. Just give me a second. Is there an easier way of muting this? Let's see. Is there like a control shift function? It's Alt A. Let's try that. Alt. I've returned. Okay. Let's see. So we did that one. There are 3 more. And the next ones are a little more obscure. They're ones that I probably don't have memorized too well. So the next one is the integral of cosecant squared u du. Sorry, that u should be closer to the cosecant. Apologies. Equals minus cotangent u plus c. So the good thing about these is that, you got your textbook, you got your PowerPoint, you got the, what are they called? You got the formula sheets posted online. And for my North Bay students, I promise I will print those off for you, obviously after all of this is settled. Let's see. Okay, so I'm just saying the good thing is you don't have to memorize these, or at least you should be familiar with some of them, so that you can at least kind of recognize when to use them. And then the next one is integral of secant u tan u du equals secant u plus c. Okay, well, that's kind of an easy one. Yes, like I think I mentioned this before, but for some reason secant and tan are always interconnected. So that's one way of kind of remembering a lot of these. Like you got the secant squared and the tan, and then you got the secant tan and the secant. They're always intermingled together. And then same with cosecant and cotangent. And then the last one is, cosecant u cotangent u du equals minus cosecant u plus c. So that is our last integral formula. There will be more of them, but they were kind of smart enough to just separate it into another section so that people wouldn't be overwhelmed. Plus the next section, they're not really integral formulas, they're just generic trig formulas that can be used as you're solving integral formulas. But that's what we got for this section, all these formulas. So let's do some of the examples. Let's take a look. This one's a fairly straightforward one. Let's look at this one. Okay. So this one is page 860. Oh, I feel so bad the banana is just sitting there all alone. I'm sorry, banana. Okay, so 860, example number 1. Integrate the integral of x secant squared x. Secant squared x squared. Oh, we got a little twist there, dx. Okay, so this one doesn't look too bad. It is one of those ones that initially looks a bit weird because you're gonna have to do a little bit of rearranging for this. The good thing is that you do have a formula for secant squared. You already just straight up directly have that formula, so that's good. So really all you have to do is just check to make sure that it's in the correct form, that it's secant squared of a thing with the derivative of that thing sitting next to it. So I'm going to do kind of the obvious. I'm just going to take the x and move it next to the dx. I just prefer doing it that way because we're going to have to move that over there anyways. And then we'll start digging in and seeing what we got. So that's the same thing, just rearranged. I should probably brackets around this just because there's a couple of x's next to each other. Okay, now let's establish du and see if we have to make any adjustments. I have a feeling we'll have to make a little one. So u is x squared. U is just whatever is sitting inside the trig function. So du is equal to, so derivative of x squared is 2x dx. So this is good news because we do have an x dx in our original integral. We just need a 2 in there. So as per usual, just stick a 2 in there and offset it by a 1/2 outside the integral. So let's do that. So 1/2 integral secant squared x squared bracket, and then we got our new 2 right here, x dx. So now it's perfectly good to go. It is in the form, in this case, it's specifically in the form 1/2 integral of secant squared u du. So it is in that form, and now you simply refer to your list of formulas. I always find it funny when you incidentally repeat a similar word. It's a really funny joke in Austin Powers that every single movie he accidentally repeats himself like that. Like he says, allow myself to introduce myself. And then the third one, he's like, what do you know about my father's whereabouts? And then I can't remember what happened in the second one, but there must be one in the second one. Anyways, I'm sorry, I get distracted easily when I'm teaching alone. So this one is tan u plus c. And then of course you'll have the 1/2 sitting there. So tan u, and I'm just reading this off of the formula sheet, plus c. And then of course, substitute u for the original variable. With this whole u substitution thing, I just do that kind of for illustration. I think it makes it a little bit easier, and it's easier to see the application of the formula. I guess you don't technically have to do it that way. A lot of people in this case could just see that you need an adjustment, and then they could just directly apply the formula. In that case, I'll give you full marks if you get the exact correct answer and if I can follow your logic. So usually I don't care too much about how much work someone shows, just as long as I get the impression that they know the methods, they did it themselves, and there is some type of logic I can follow to their answer. So let's write our final answer. So 1/2, and then u was x squared plus c. And yep, that's correct. Very good, very good. So that's the first one. So that wasn't too bad. The next one is, the next one's an interesting one. Oh, actually, that's not too bad either. You kind of, let's read this for a second. So you got that, you got that. Okay, let's do the next one. Getting rid of this. Example number 2. Integration of tan u secant u du. Okay, so it says integrate, and this one initially looks very, very weird. Yeah, it doesn't look like you could apply a standard trig formula to it. So you got tan, you got cos 2x, and then you got dx right here. Okay, let's see. Okay, so for this one, like I said, it's a bit of a weird one. There's a lot of avenues you could go down to try to solve this one, like if you were just spitballing. Like one thing that I might try is the fact that tan, by definition, is equal to sine over cos. So you could try subbing that in and rearranging a bunch of stuff. But I have a feeling it probably won't work that well. One thing that you could recognize is that the inverse function of cos, like not the inverse, I'm sorry, the reciprocal, which is different. It's like the flipped version of cos, is secant. So that's probably where I would start, because if you want to, you could change the cos on the bottom and you could put it up to the top and change it to secant. You're allowed to switch stuff as long as you switch it to its appropriate reciprocal function. I would probably do it that way, because then you're going to have a tan and a secant, which right off the bat is good because those are always interconnected and there will probably be a formula for that. So that would be my logic as to how I would get there. So let's do that. So integral tan 2x, and then cos, you could bring it up to the top and change it to secant 2x, and then you got your dx as well. And again, that's just because secant is the reciprocal function of cos. You could have done the same thing with sine. You could have moved it up to the top and changed it to cosecant if there was a sine in there. Okay, so now let's kind of regroup and take a look at what we have. Is there just a formula for this? Tan and secant. Yes, there is. The integral should just be secant. So that's very nice. That's convenient. So we could just directly apply the formula. There is one tiny additional problem. You might notice that instead of x's in these functions, we have 2 x's. So in this case, you got to take that into consideration because you're going to have to make a little bit of an adjustment. So let me show you. In this case, u is whatever is inside our functions. It's 2x. And then du is equal to 2 dx. So that is one thing that we have to do because we don't have a 2 dx, we just have a dx. So we're going to have to make an adjustment. So whenever you see numbers in your trig functions in that regard, you do have to go through your usual practice of establishing u and making any adjustments, because in all of those cases, you're going to have to adjust for that particular number. And once you get really used to it, you could just see the number, insert it by the dx, offset it outside the integral. A lot of the times you could just do it in kind of 2 seconds once you get really, really used to it. So let's put a 2x in here, or a 2 rather. We'll have a 2 dx in there. So integral of tan 2x secant 2x, and then I'll put brackets and then 2 dx. So I just inserted this 2, so I got to put a 1/2 out here. Oh, someone raised their hand. Go ahead with your mic if you want.
Yeah. How did you determine the what u was?
U is whatever is inside of your trig functions.
So what if they were
So,
different? Would they ever be different? Like, I know they're both 2x in this.
Oh, good question. Like, would it be 2x and like 3x or something like that?
Yeah, whatever, yeah.
The short answer would be no.
Oh, it would never be that.
I don't think that would be, I think that would be beyond the scope of the course. I don't think I've seen a question like that.
Okay.
But it's a good question. In that case, I wonder what you would, that would be a weird one. You'd have to, for that one, you'd have to use more advanced trig identities. So the short answer is, don't worry about it.
Cool.
Okie doke. Let's see. So, oh, and now we could just directly integrate this. So 1/2, and the integral formula says that it is secant u, and everything looks good. Everything's, yeah, it's the same as the formula. Yeah, okay. So that'll be secant u plus c. And now let's put in our original 2x. So 1/2 secant 2x plus c. And yeah, so very good. And just to kind of expand in a general way on the previous question, in regard to u, it pretty much all depends on what formula they give you. The formula makes it clear exactly what you're going to pick for u. Let me just write down the formula that we just used. It was this one right here. So as you can see, u is just whatever's inside these trig functions, and it's all just the same variable. So if they were different, the formula wouldn't even, what was that? That's weird. My screen fell off. Oh well. Yeah, if they were different, the formula wouldn't even, it doesn't even seem like the formula would apply. What else do we have? We got that one. That one looks like a lot of work. Yeesh. Let me see. Let's look at something else. Wow, why is that so long? Oh, okay, so they're kind of explaining how they're deriving various formulas. Okay, so the next part it has in the textbook is it gives you 4 more formulas. And yeah, like I said, I have a feeling they're just kind of breaking them up so that people don't get overwhelmed by seeing an entire page of formulas. So 4 more formulas. These ones aren't too bad. They're kind of interesting. Let's look at them. Where's my mouse? Let's get rid of this. Okay, so here are a couple more integral formulas. And maybe we'll prove one of these because I think they're pretty easy to prove, at least comparatively easy within the realm of calculus. The first one is tan u du, and that's equal to minus ln of absolute value cos u plus c. So that's kind of an interesting formula because you're, darn it, sorry, give me a second. Apologies. Yeah, it's kind of an interesting formula because like it's going from trig to a ln function with a trig function embedded inside of it. It's kind of cool. So let's go through the other 3. They're all pretty, I mean, they're pretty arbitrary formulas. And then I think I'll prove this first one just for fun, because I think the proof is, I'm just doing it. Yeah, it's a really short proof. Let's see. Next one is integral of cotangent u du, and that's equal to ln of sine u plus c. So that one's very similar to the previous one. And then the next one is a bit of an uglier formula. I guess I shouldn't call formulas ugly. Formulas have feelings too. Secant u du is equal to ln of absolute value of secant u plus tan u. So that's a neat one, the fact that you got 2 of them added in there. And last one, cosecant u du is equal to ln of absolute value cosecant u minus cotangent u and the absolute value plus your constant. So those are our 4 new fancy formulas. And yeah, so like I said, let's go to the first one and prove that one. The way to prove it is fairly straightforward. You just take, what we're going to do is, of course, what we typically do, we'll just take this part and take the derivative. And if it's a correct formula, it should regress back to exactly what we have inside the original integral, since, of course, an integral can be thought of as an antiderivative. So that's always the way you could check stuff. Take derivative of the answer, and it should return you back to what was in the integral. So I'm just going to erase all of this so we have some room. So let's write this off to the side. This is what we're trying to prove. That tan, and this part right here is just for fun, just for illustration, equals minus ln of cos u plus c. Okay, how do we prove this? Okay, so let's start where I said we would start. Let's take the derivative of minus ln of absolute value cos u. At that point, you don't have to worry about the constant because it'll just diminish to 0. That's the reason that constant's there in the first place, because the derivative of constant is 0. So that's why you always got to have that hypothetical constant there that could have, I guess you could think of, it could have been originally there. Okay, so let's take the derivative of this. So I'm just going to write out minus ln, just to get my bearings, cos u, and I'm just going to do a big derivative sign right here. So the derivative of ln, I'm trying to recall, is that the inside function drops down, and then you have the derivative of the inside function on top. Yes, that sounds right. And then the minus sign will just sit there. I'll just put the minus sign, just whatever, right here. So original function drops down, cos u, and then on top you have the derivative of the function. So derivative of cos is minus sign. So you're going to end up with 2 minus signs here, the original one and the one from taking the derivative of cos. And again, this is just using the previous derivative ln formula that we looked at before. So a couple of obvious things, your little 2 minus signs cancel each other out. Goodbye, minus signs. And then sine over cos, surprise, surprise, by definition, is tan. And that's exactly what we have in our integral. We got tan, or you could say tan du, tomato, tomato in this case. So the proof is actually only like 2 lines. So hopefully this at least illustrates the logic of the formula, because when you look at it, you're like, what the heck are they doing with this formula? But it actually, it works perfectly. What else? Hi, banana. Let's do, I think we'll take a, we'll do, oh, we're almost done this entire section. Okay, we'll finish the section, then we'll take a break, and then we'll figure out what to do next. Okay, so next example, let's get rid of this. So this is example number 4. And my advice for practicing these is that I would do what I did in university. Just even if we'd done the example, just look at the actual example without looking at the solution, try it yourself. And then at least that way you're starting off with stuff where you could check the answer and not get frustrated. And then start with some of the easy exercises and then go from there. I always thought that was the best way of doing it. Example 4. Sorry, I got to pause it another second. Apologies. Okie doke. Let's do, yes, number 4. So this is integrate the integral of tan 4 theta d theta. So this one looks really, really yeah, it looks like there's not much to this one. What's the point of this one? Yeah, all you have to do is just, okay, well, I guess they just wanted to kind of illustrate a nice example. Okay, so let's check our formulas. There is a direct tan formula. It was the one that we just proved. So the only thing you have to worry about is just the fact that you have a 4 theta rather than just a theta. So you're gonna have to make a bit of an adjustment. And again, once you get really used to these, you could kind of just know that, like in this case, you're gonna end up just inserting a 4, offsetting it by 1/4, and then you could directly use the formula. But again, let's stay consistent and let's stay formal. So U is 4 theta. So du du should be 4 d theta. So we need a 4 in there by the d theta. So let's do that. And then we'll offset it as well. So tan 4 theta. And then I'll put a bracket and then 4 d theta. And then I'll offset it by 1/4. Good. And then, yeah, I guess that's all we have to do. And then we could just directly apply the formula. Good. So the formula is, so I'll keep the 1/4 here. The formula is minus ln of cos u. So I'm going to put the minus just right here, just for simplicity. It just looks better just sitting in front of the number. And then ln, absolute value, cos u plus c. And now let's put in our original 4 theta. So minus 1/4 ln absolute value cos 4 theta. So that one wasn't too bad. It was just a basic illustration of the first formula. And then you got to do your little fancy adjustments there. Ooh, and the next one's pretty neat. Maybe I should leave one for, well, I mean, we already got the participation questions. So let's do this one and then we'll take a break. Get rid of this. So this one is the integral of secant e to the minus x. Ooh, interesting twist. Dx. And then at the bottom, another twist, you got e to the x. So this one looks weird because it's like a thing over another thing, and none of the formulas had that. One really good thing is the fact that you do have a direct secant formula, because sometimes you don't even have a direct formula for what they're giving you. So you got to do like a bunch of work. At least in this case, you could quickly see, oh, there is a secant formula. That's a good way to start off. Now we just got to make sure it's in the correct form. So what would throw people off here is the fact that we got these e to the x's. So I got to think for a second about how we're going to handle these. I think the best thing to do would be to take the bottom e to the x and move it to the top and change it to e to the minus x. Again, you're allowed to change a number from the bottom to the top as long as you change the sign on the exponent. I think that would be a lot easier. It would look more familiar to us. So let's do that, and let's regroup after that. Integral of secant e to the minus x. And then if we bring the e to the x up, it'll also be an e to the minus x, and then we got dx. And the reason I have a habit of putting brackets around certain parts is because I just want it to be clear to the reader that this first e to the minus x right here is inside of the secant. Everything else is outside of it. So brackets help clarify that to the reader. What should we do now? Now let's just, and when in doubt, just go through the process, assign u as whatever's inside the integral formula, find du, and just see if you got to make any adjustments. Okay, so u, and we will have to make, it'll look like we'll have to make one small adjustment. So u is e to the minus x. So what's the derivative of that? The derivative of that is itself. First of all, it's going to be e to the minus x. But then since you have a minus x, there's going to be a minus that pops out. It's called the chain rule. Whenever you have a function embedded in a function, you take the derivative of the original function, which in this case is e, or a generic exponential function. And then after that, you got to take the derivative of the quote inside function, which is your little minus x. So minus is going to pop out. You always got to remember that little chain rule. It's like rushing nesting dolls. And then you got your dx. Okay, so in the original function, we don't have a minus sign. So we need a minus sign. And just so I don't have to keep rewriting this, I'm just going to insert it right here. So I'm literally just going to put minus right here and minus outside of it as well, so that the two minus signs would hypothetically cancel, because you always got to keep everything balanced. And I guess that's, I guess we could apply the formula now. So minus sign in the front is going to sit there. And what is the formula? It is ln of absolute value secant u plus tan of u plus c. And yeah, now we got to put in the original, let's put in the original variables. So u is e to the minus x. So secant e to the minus x plus tan e to the minus x and your absolute value plus your constant. So that's what you get in this case. So this one, again, isn't too bad. This is one of the ones where you need to know those little tiny tricks in order to kind of make the question easier. Okay, I think it's time for a break. Let's take a bit of a longer one. Let's just come back at 10:30. So it's 10:17 right now. So everyone come back in about 13 minutes. Recording. Kind of an update. I'm going to put up assignment number 1B as well. Yeah, it's logarithmic and exponential forms. So we've gone through those. So I think I'll make that due next Thursday, and then I'll probably just post a PDF of the solutions a few days later, or I'll just take it up in class the following Tuesday. So I'll put this all in writing because I realize that there's multiple dates to keep track of. So the simplest way to state it is that first assignment due Tuesday, I'll take up the solutions a few days later. Second assignment due Thursday, and I'll present the solutions a few days later. So I'll put that all on Brightspace. So 2 assignments to work on. If anyone has any questions or gets stuck on anything, please let me know, send me an email. I'm just trying to think of what else. And I'm just trying to think of if we should cover anything else, because that was like a solid amount of examples. And the next section, some of these questions get really long, and I think we'd only be able to cover like one of them. So
I have a question about the first assignment.
Sorry?
I have a question about the first assignment. When's a good time to ask?
Oh, right now is perfect.
Okay, it's just about like the way, like the question 2, where it's cotangent 7x to the 7x and over sine squared x dx.
Okay, let me just bring up that assignment. So it is, so that's number 2, right?
Yeah.
Okay. Yeah, that's a weird one. Yeah, typically, usually people have a bit of trouble with this one, so it's good to ask. Let's read this. Rewrite, and then I'll write it down in the whiteboard. Rewrite the given integral so that it fits the form. Actually, hold on. Let me bring up. Give me a second. Where is this? This one. Okay, so let's go to whiteboard. Share screen. Get rid of this. Okay, so this is rewrite the given integral so that it fits in the form integral of u to the n du. And identify u du and n. Okay, so this is one of the ones where it looks really, oh, first of all, I should write the actual question, geez. It is cotangent, my eyesight is so bad, cotangent 7x over sine,
Squared.
what is that?
Squared.
Sine squared, okay. Sorry, when I'm tired, my vision gets blurry. Cotangent 7x over sine squared x dx. Okay, in this case, let me bring up, because there's a couple of things that you could note in this case, and those will allow you to do a couple of those. There's really only one little trick to do here, and then the rest of it ends up being a bit more straightforward. I'm just going to bring up my kind of generic formula sheet that has all the derivative formulas on it. Okay, so the first thing, oh, actually I need two different sheets. Yes, okay. So the first thing I would note is that sine is the reciprocal of cosecant. That's one little thing you can note. Let me write that here. I'll write all these little notes in the, so sine x is equal to 1 over cosecant. So that gives you a bit of freedom in this case, in the sense that if you want to, for whatever reason, you could replace sine squared with cosecant squared as long as you moved it up to the top. Now, whether or not that's a logical thing to do remains to be seen. So let's check out what the derivative of u is in this case. So u is cotangent. And if the derivative involves a cosecant, then we're probably golden. So let's set cotangent equal to u, and du, oh, it should be cotangent x, sorry. And du is, so what is the derivative of cotangent? Let's look this up. Let's see. Derivative of cotangent, where's that listed? Come on,
Negative
where are you?
cosecant squared x.
Say that again.
Negative cosecant squared x.
Perfect. Negative cosecant squared x. Okay, so in this case, it looks like a good plan of attack would be to take the sine, move it up to the top, so you got a, in this case, you'll get a minus cosecant squared, which is actually the derivative of cotangent. So in this case, you will have u raised to some exponent with the derivative of u sitting right next to it. So let's do that and let's see how it looks. Integral of cotangent 7x. And then we got, so you can bring the sine squared up to the top and change it to cosecant squared. And remember, with the reciprocal functions, you could always do that little trick of switching them to the top or the bottom of the top and whatnot. So now it looks like this is nearly in a good form. It's in the form u to the 7. We don't quite have du sitting next to it because we need a negative sign. We need this whole thing, including the negative sign. So the only adjustment you would have to make is put a negative sign here. Let's put some brackets around here. Put a negative sign here. And then at this point, you could kind of just directly compare it to the formula and deduce what u is, what n is, and then what du is. So I don't want to give away the whole question, but hopefully this helps. Yeah. So did that clarify it, or do you want me to, where are you at?
No, that's good for me.
Okay. Yeah, because
you.
in this case, of course, it's just like compare this to this, compare this to this, and compare this to this, and those are the things that it asked for. And you don't even have to solve it. All it wanted was just u and n and du, and it doesn't even ask you to solve it. So once you state u and n and du, you're good to go. Good question. Does anyone have any other questions? Okay, so this will all be, all the assignment stuff will be in writing. I won't do any more participation because we've already done 2 of those. Okay, let's stop the share. Someone wrote, could you write du as dx over sine to the sine squared x? Could you write it as dx over, and that's, okay, hold on, let's see. And let's go back to the share. Where was that? Whiteboard. So in this case, yeah, I wouldn't recommend doing that, because if you, for example, if you tried just doing that right off the bat, and you tried just saying that u is dx over sine squared x, it really sucks to try to take the derivative of that. What would be the derivative of that? It would just, yeah, it's, I don't think it would bring you down an easier avenue to keep it like that. I think it would be best to do that early maneuver where you bring it up to the top, because then you directly have du sitting right next to u. If you do it this way, it doesn't quite look like that. It's a bit harder to take the derivative. So I would stick with the original method on that one. Okay, but this kind of, it's a good example because it illustrates that, like, in this case, it just completely doesn't look like it's in the correct form. And then you just do one little trick, which is the trick of bringing sine up to the top. And then it's a little more clear that it actually applies to the formula and that it's actually in the correct form. Any other questions? Oh, my chat disappeared. Where did it go? Chat. Okay. Okay, so I guess that's everything for today. So everyone have a good day and a great weekend. And for everyone, I'll keep you updated on whether or not we're having a regular class or an online class on Tuesday. I'll let you know as soon as I know. Have a good one.